A scatter plot is a collection of XY coordinate pairs that are plotted on a coordinate plane to allow us to look at and try to understand visually the pattern and behavior of those pairs of points, or those pairs of coordinates. The first thing we can look at when we look at the scatter plot on the left and the right here is the general pattern that they're following. The dots that we have on the left follow a pattern that's mostly linear. That may not be the line of best fit drawn through those points, but it's an approximate line. And we can see that while those points don't follow a perfectly straight line, they're generally following a linear pattern. If we look at the points on the right, a straight line really wouldn't connect through all of those nearly as well. What we actually see is this set of points is following more of a curve. Which again, I might not be drawing the curve of best fit there, but if we want to draw a curve that passes through those different points, or draw a shape that passes through all those points, we definitely end up with more of a curved shape. For now, we want to focus specifically on the cases where our points do come out to follow this linear pattern. Later in the semester, we'll come back to these ideas of nonlinear patterns and see what we can do with those. Looking at our graph on the left again, we can see that, again, we have that linear pattern, and we also have what we would refer to as an increasing pattern. So as our x values move from left to right, those dots are following a generally increasing pattern. If we had a different set of points that were still following a roughly linear pattern, we could also see a case where as we move as our x value changes or moves from left to right, we would see a decreasing pattern. We can measure the strength of the association, or essentially how well our data fits to that straight line pattern, by calculating something referred to as the correlation coefficient. The correlation coefficient is going to be equal to lowercase r, and will always be a value between -1 and +1. In the case of our first equation, those first dots that we had plotted, the correlation coefficient for that data would be 0.9268. So what we have is a value that's very close to 1, meaning a straight line pattern would be a very good fit for that data, and the value is very close to +1, meaning we're seeing an increase, that increasing behavior as we move from left to right. The second set of points, the ones that I just added there, would have a value, I just made up these points, but this would be something closer to, say, -0.9. So in this case, the value is very close to -1, meaning this is still a very good fit. This linear model would still be a very good fit for our data. But in this case, that negative is telling us that we're seeing a decreasing pattern as we move from left to right. So as our value for the correlation coefficient gets closer to either -1 or +1, that's telling us that we have a very strong fit. And as our value gets closer to 0, that means we have a very bad fit for that linear model. So the only difference between a value very close to +1 and a value very close to -1 is, again, just the direction of that relationship. We're either seeing an increasing or a decreasing pattern. In example 6, we're given the actual data that was used to construct that first model. So we're going to switch over to Desmos and look at how we can enter this data and construct that linear model. Actually, I'm sorry, we won't look at constructing that linear model quite yet. We're just going to look at how we can plot those points to construct our scatter plot. So I've already pulled up Desmos.com, which is freely accessible. Once you open this up, you can just click to start graphing. You could create an account, or if you already have one, sign in if you've used this before, which would allow you to save the work that you complete, but nothing that we need to do right now. We're just demoing how we use this information. Clicking on, or how we use this tool. Clicking on the plus sign, I can select Table, which will already populate values for titles of X1 and Y1 for my 2 columns, which will allow me to start entering in the values in this table. So what we'll enter in will be first 50.3, and then either pressing Tab or the right arrow key, or simply just clicking in that next box, we can move over to enter that corresponding value for calories of 42.4 or 424.2. Pressing Tab again will move me down to that next row, and I can enter in that next row of data. And I'm going to continue doing that, but I'm going to go ahead and pause the video just to save some video time here, and I'll pick back up once I've got that data entered in. I finished entering in all that data, and hopefully you pause to go ahead and do that as well. And what we notice is we don't see anything on this graph, because right now our window setting isn't set to match up the different points that we've plotted. If we look back at that graph that we had on our notes, we can pull values for X and Y straight off of that. If we click on this wrench icon over on the right, this will allow us to change those minimum values for X and Y. So the graph that we had in our notes was going from an X value of 0 to 70. And for our Y values, this was going from 0 to about 500. So by changing those values for X and Y, now we can actually see where these points are getting plotted. In addition, we can use the plus and minus buttons to zoom in and out. If your mouse has a scroll wheel or some scroll function, you can also use that to move in and out. But basically, we just need to adjust our viewing window so that we can actually see those points plotted. In our remaining examples, then we'll go ahead and take a look at how we can construct those linear models and make use of those in terms of some actual applications.